we talk about the shape of an object, it is often helpful to distinguish between the notions of its interior, or the space that is inside the object, and its exterior, or the space that is outside of the object. The boundary of a shape is the separation between its interior and its exterior, denoted by this symbol. The medial axis transform, shown on the left, describes the shape of an object in a different way. Instead of the boundary, it uses a skeletal structure consisting of medial branches and junctions. The medial axis transform can be considered to be dual to the boundary representation, much like how the Voronoi diagram is dual to the Delaunay triangulation. They both contain the same information, but exposed in a different way. And depending on your application, you'll find that one has better properties than the other. The datasets that we encounter in practice are almost always distributed using the boundary representation. For instance, a point cloud, a tin, or a regular grid. So, given the boundary of an object, how do we obtain the medial axis transform? There are two equivalent definitions that describe how to obtain the medial axis transform from the boundary. One is based on a crossfire analogy, and the other is based on so-called medial balls. In the crossfire analogy, we imagine that the whole boundary is set on fire at the same time. The fire spreads with a constant speed away from the boundary. The isolines in this image can be seen as the shape of the fire front at different instances in time, as the fire travels away from the boundary towards the middle of the object. The medial axis transform, shown in blue here, appears where the fire front meets itself. The second definition of the medial axis transform is based on medial balls. A medial ball is a ball that fits completely inside the object and is not contained by any other balls that fit inside the object. For instance, this ball is not a medial ball because it is partially outside the object. And this is also not a medial ball because even though it fits inside the object, I can draw another ball around it that also fits inside the object. This ball, however, is a medial ball. Notice how it touches the boundary in 2 points. Now, the medial axis transform is defined by the center points of all medial balls of the object. Medial balls can also be defined for the exterior of an object. This means there are 2 parts of the medial axis transform, the interior MAT and the exterior MAT. This animation illustrates the shrinking ball algorithm. For each boundary point, a medial ball is found through an iterative process. In each iteration, a smaller ball is found by searching for the nearest boundary point from the center of the current ball. All candidate balls are centered on the line through the normal vector of the boundary point. The algorithm terminates when an empty ball is found. This ball is considered to be the medial ball of the boundary point. By flipping the orientation of the normal vectors, both the interior and the exterior balls are found. The shrinking ball algorithm works well for terrain point clouds, such as this one. With the shrinking ball algorithm, we can compute the interior MAT and the exterior MAT. Notice how the medial branches or sheets delineate the ridges and valleys in the terrain.